system with finite horizon goal. He's my PhD student. Give him a hard time.
Yeah, so thanks for that introduction, I think. Right, so multi-agent systems with finite horizon goals. I'm Senthil, and as Moshe said, this is joint work with him and his PhD student over at Rice. So first, a little bit background on some reactive systems. Now, Laurent had a very similar picture in his slide deck, but I'm going to go over this one really quick too. So this is kind of your classic reactive system setting. You have two agents, a system and an environment, and they both have control over some set of variables. So one has control over the controlled variables, we call it the system. The other one has control over the uncontrolled variables, so they're uncontrolled because they're not controlled by the system. And together, at each one of these time steps, they will assign a setting to their variables, which will then go to like kind of this collective pool that's fully observable. And the idea is that this game is played by a system who wants to achieve some sort of temporal specification and an environment who just doesn't want that to happen. I'm assuming that this setting is very familiar to most of you. But yeah, this is the very classic reactive system setting. So now let's talk about what that temporal specification might be. Well, usually it's in the literature especially, it's going to be some sort of temporal logic. And that just is a logic that reasons about, logical properties that have a temporal element, as again, I'm sure any of you know. But the new thing kind of here is that, well, first you had an infinite horizon logic, like something like LTL, and that modeled infinite time models, that had infinite time models, so really just of one length, of infinite length. And that was really the dominant force in the previous literature. So it was very popular in the previous literature, but recently we've discovered, we've kind of invented, I don't know what we should really call it, these finite horizon logics, and that was done by Moshe Vardi and Giuseppe Giacomo. And these represent specifications that hold over some finite discrete number of time steps, right? Instead of an infinite amount like this. And it could be a different number. Like, for example, you have one model of length 5, and you have one model of length 3. And they've been recently developed, well, recently compared to this, and they've been gaining a lot of popularity. So I'll say, why should we consider finite horizon goals, right? And I think the answer is that many tasks are truly finite horizon in nature. Like if we want to route this robot from here to there, then it's done after a certain point. And, I think it makes sense to terminate kind of what we're looking at after that point. So the idea is that if you have a task that involves something that's like completion, like reaching a goal or even reaching a final configuration, then the semantics of a finite horizon logic that terminates after a certain amount of time kind of make more sense to it. And also you have this idea that finite horizon logics are reasoned about through finite word automaton, right? And that's easier in general from a complexity-theoretic standpoint to reason about than their infinite word counterparts, which is what we used for, say, LTL algorithms, for example. And I'd just like to bring up here that there was one of these triple AI Spring Symposium workshops. It was specifically dedicated to how effective temporal logic was in AI. I went to it. It was a good time. And that was just last year. So it's a really new, relatively new, and very burgeoning field. Now, if we're going to consider a temporal logic that is a finite temporal logic, like LTLF, for example, then we can think of kind of three different automata representations for it. So if we have the formula phi at the top here, then you can see that there's kind of three different representations that it could have in general. So the first is that there's a linear transformation to this alternating finite automata. There's an exponential translation in the worst case to this non-deterministic finite automata. And then there's a doubly exponential translation to this deterministic finite automata. Now, non-deterministic automata, I'm assuming that most of you are familiar with. They have kind of transitions from, you can take multiple transitions to the same input. But an alternating finite automata, it may be a little bit different and maybe kind of new for some of you, which is in addition to non-deterministic transitions, you have alternating transitions. So whereas the non-deterministic automata can choose kind of the best transition for acceptance, the alternating automata has a different type of state called an alternating state, in which you can think of it informally as being the worst possible one chosen. So it's kind of almost like a two-player game. One person chooses for acceptance, one person chooses for non-acceptance. And they are exponentially more succinct than the others in this like kind of hierarchy way. So let's talk about what it would mean to solve these types of games. There's reactive synthesis, the games that are induced from this, right? So first, I'll say that a very typical notion of a strategy is this finite state transducer. So a finite state transducer is a deterministic automaton in which each state is associated with an output. So the input to this automaton will be the collective setting of that variables. So everything you observed from the past, from the system and the environment, that would be one transition. So you take that input, it would maybe move from here to here. Well, those are the only two states I drew, so I guess it would have to. And each state is associated with an output. So there'd be an output when you go to this state, there'd be an output to go to this state. And so, for example, the system, it would take its input, both the system variables and the environment variables, but at each state, it would only output what it wants to do for the system variables, right? And for reactive synthesis, for active systems and reactive synthesis, the system agent wants to satisfy that temporal specification. So the solution concept we're going to be using is called a winning strategy. That's a system for the strategy such that no strategy for the environment can make that temporal specification untrue. It's a strategy that's always winning. And we know such things always exist for either the system or the environment. And the two big problems in this area, I would say, are verification, which is that if we're given a strategy for the system, we want to determine if that's a winning strategy or not. And also realizability, in which we determine whether the system has a winning strategy or not, because the environment might also have a winning strategy. So these are the two big problems that we're going to be studying throughout, and this is how they correspond to reactive synthesis. So here we have our first little kind of table of results here. And we had to kind of fill this in, Moshe and I, because they are kind of somewhat standard reductions, but you kind of have to piece together things because not so many things are phrased in this exact setting that I told you, but it is highly related to some problems that have already been studied for a very long time. So if we look for the realizability column first, then a deterministic finite automaton, if the system has a DFA specification and it wants to satisfy this with an environment who doesn't want that to be satisfied, this can kind of be thought of as a reachability game, and that's going to be p time complete. Then going down this list, we have x time over p space, so there was a gap. And that's because you can do the subset construction for NFAs, and you can reduce from universality for NFAs as well, but it was not known if it's actually in p space or if it's in x time. And then for the alternating finite automata, well, this is largely inherited from the logical specification itself. So you might know, for example, that LTLF satisfiability, or I mean realizability, I'm sorry, is 2x time complete. And since there's a linear translation back and forth, this is largely the same thing. So we can see almost a very nice progression here. We have p time, maybe x time, right? And then double x time. So that's kind of a very clear thing, is that as the goal becomes exponentially more succinct, the complexity jumps in exponential class. On the left-hand side here, for the verification problem, that's where the system is already committed to a strategy. So we can kind of think of this as being the environment wants to reach an unaccepting state or keep you there, which is kind of like ST reachability, the classical NL complete problem. And then for this, you can kind of reduce from p-space completeness to mostly NFA universality. And the interesting one here is that verification for AFA is x-space complete. Now, for some of you, that might look weird if you're kind of familiar with the results for LTL. You would think this would be p-space complete, but it is in fact x-space complete. It is in fact weird, and this is the kind of citation you can use for that. It was proven by a former lab member, Suleiman von Saal, and her co-authors, and pretty recently too, 2023. That was at ADVA. So let's talk about multi-agent systems now, and we're going to take that reactive system setting and just generalize it in kind of, I would say, a very straightforward and natural way. So the first thing I want to say is that the concept of winning strategy doesn't really make sense anymore because there are multiple agents. Winning for who? Winning against who? So we have kind of n agents. I only drew 3 here, but this ... kind of implies that there's more. And each agent has its own specification. So it comes with its own specification that it wants to satisfy. So this is agent 1 specification, agent 2 specification, and agent 3 specification. They're all going to have their own variables. And once, just like before, they're going to set their own variable setting. And I want to point out that this is basically the iterated Boolean game model that was introduced by Julian Gutierrez and his co-authors in 2015. So if we can't use the winning strategy solution concept, then what should we use? Well, I think the natural choice is the Nash equilibrium. which is probably the most popular multi-agent solution concept. Kind of a tongue twister. So we would say that a profile of strategies is a Nash equilibrium if no agent can unilaterally deviate, change its own strategy to increase their own payoff, right? And so here we have a special setting. We have a temporal specification, which can either be satisfied or not satisfied. So increase their own payoff means basically that you can go from not having your goal met to having your goal met, right? So again, agents that have their goal met on their deterministic execution of this system, again, we're talking about deterministic strategies, um, then receive the highest possible payoff, and they aren't interested in deviating. But agents that do not meet their goal when the strategies are followed, they shouldn't be able to change their strategy profile, so they can't change from this action to this action, where this would be an accepting state for them, because that would be bad, right? That would be the idea that they could deviate in order to change their payoff. So the way we were able to kind of think about this, and just as a primer before we get into the rest of this, is that we did analysis through two different components, right? So the first thing we did that was kind of a little bit different was that we specified a WNE. Now, what does that mean? So because there are only two possible payoffs, you can either have your goal satisfied or you can have your goal not satisfied, then payoffs would either be 1 or 0. You could think of them as being like that, right? So we would specify beforehand which agents we would expect it to have a payoff of 1. And then if you wanted to kind of see if any sort of Nash equilibrium existed or if maximal W existed where maximal ones were achieved, then you could kind of iterate through all of them. So that led to two different conditions that we could separate out. The first is the primary trace condition. That is, if no agent deviates, do we get the behavior that we expect? Do the agents in W meet their goal and the agents outside of W not meet their goal? The next one is the deviation condition, which is that if an agent not in W decides to deviate, are they able to improve their own payoff, right? So we were able to separate out these two conditions, and that's a kind of major point in the complexity theoretic analysis that will follow. And it's also a primer of just how to think about this in general. So again, we have the two major questions here, verification and realizability, but they're going to look a little different because the setting is a little different, right? So, but I mean, so like if we're given a strategy for all the agents, not just the system, and again, as a parallel to reactive systems, we have to check if it's a Nash equilibrium or a W Nash equilibrium. And then realizability is we determine whether such a Nash equilibrium exists. And why are we asking these questions? Well, I really want to know what drives the complexity of analyzing multi-agent systems. Is it the goal representation? Is it the complexity from having a bunch of agents interact with each other? Well, what could it be, right? Hopefully by the end of this presentation, we'll get a good grasp on that, right? Because so first I want to talk about the realizability results for multi-agent systems, right? We can see here we have a little bit of a different picture. We have P space for the DFA, X time complete for the NFA, and 2x time complete for the AFA, right? And before I go on any further, I should mention that there were previous results by Gutierrez, the same one who introduced the iterated Boolean game model in 2017. He started with an LDLF formula, which is kind of like starting with an AFA. And he showed that the realizability problem belonged to 2x time. So there was 2x time membership for that problem. And I want to point out that, this was a good result and a good paper, but the cost of this was mostly just done about realizing the LDLF, realizing about that temporal specification in the first place. They're kind of so compact that just unfold them to reason about them, you already incur this WX time blowup, which means that actually reasoning about the Nash equilibrium afterwards kind of gets lost in the shadow if you already eat that blowup at the very beginning, right? So I would just like to point that out. Oh, and these are, And I would also like to point out that I introduced that gap before, that was X time over P space, but the reduction we're going to do and the reduction we're going to show here will actually show that it is X time complete, which settles the open problem of what the actual complexity of that was. So here we have our complete picture. We have P space, X time, and 2X time. Again, it almost looks like we have an exponential blow up between the succinctness of the goals, except we're starting at P space where one would expect P time, right? But we can clearly see that the more succinct the goal is, it does indeed matter for the complexity because these classes are different, and we really think these classes are different, right? So, yeah, we think they are, right? I mean, probably. So the first thing I'd like to talk about is the upper bound for the DFA realizability. And basically, what we were able to do is because we were able to separate out those two components of the analysis, the primary trace condition and the deviating trace condition, we were able to build a very special top-down Buki tree automaton, and that was able to be tested. We were able to reduce non-emptiness of this tree automaton to non-emptiness of an exponentially sized Buki word automaton. Again, I don't want to go too much into the details, but it was really the special nature of the separability of these two things that allowed us to do this kind of analysis. And if you've maybe I just like this algorithm, so I decided to draw a picture of it, which was how you test a Buki word automaton for non-emptiness. Well, you can first guess a path in the automaton, and then you guess a cycle, and that cycle should contain an accepting state. And since you're only pretty much guessing one thing at a time and maybe remembering where your cycle starts in addition to that, you're really only remembering like two states at a time. So that's in n log space or NL. I guess I referred to it as NL before, but in order to make this box fill out better, I put n log space down here. And then let's talk about the lower bound. So we wanted to reduce from, yeah. Okay, so it's an exponentially sized Buki word automaton, and you can test it for non-emptiness in n log space. So if you apply kind of the logarithm to the exponential, you get p space. Well, you get n p space, which isn't really a complexity class because it's the same thing as p space. So yeah. So how do we get the matching lower bound? Well, we wanted to do a reduction from DFA intersection non-emptiness, which is the classic, or I would say one of the canonical p-space complete problems. It's this idea of if we're given n DFAs, will they accept a common word? And so that kind of seems kind of a good place to start because we have n DFAs here and we can have n agents over here. And aside from the fact that we use prefix satisfaction and there are a couple other technical details to iron out, mostly we're going to translate the DFA into specifications that are going to be DFA specifications. And they're going to be slightly modified because, again, there are a couple of details to work out. And then the idea is it in a Nash equilibrium where every agent meets their goal? So that's going to kind of be the idea about how we can get a p-space hard lower bound for this, right? So with the upper bound and the lower bound, that shows that it's p-space complete. So now let's talk about the NFA realizability upper bound. Now, this one's very simple. If I have an NFA, I can do a subset construction and I can turn it into a DFA. And that's an exponential blow up in the worst case scenario. And that's pretty much it, right? I mean, so like if I can just play a safety game or a reachability game on an exponentially large arena, then I can do that in P time. But since I did take an exponential blow up to begin with, then I'm in X time. That's the upper bound, right? So the new part is this lower bound, and I will kind of link you later to this, but I really want to give you the high level idea here. So the idea here is to reduce from the decision problem of whether a bounded space Turing machine, alternating Turing machine accepts the empty tape. An alternating Turing machine is just like an alternating finite automaton in the fact that it has alternating states in addition to non-deterministic states. So with the non-deterministic states, the machine can transition kind of in the best way possible. You can think of that. In the alternating case, from those states, both have to be accepting, right? So if one's not, you could think of kind of an antagonistic second player as choosing the worst possible option. So the way we did this was, if you're kind of familiar with maybe how these proofs work, then instead of lining the IDs of a Turing machine vertically, we did it horizontally. So what's the idea of a Turing machine? An idea of a Turing machine is just the complete contents of the tape, along with where the head is, what it's pointing at, and what state it's in. So here, I just made it simple. I made it a two-cell tape. So here, agent 1 is responsible for kind of outputting the IDs in sequential order. So each one of these would have been an action from agent 1. So his alphabet is basically the entire alphabet of the Turing machine, along with this special symbol X, and also the cross product of the state space with the alphabet. So he can output, first for example, A and Q1B, and that means that the first cell reads A, and the second cell reads B, and also the machine is in state Q1, and also the machine is looking at the second cell. And then he will kind of output this X to say that that ID is done. And then he's going to output the rest of them. And the second agent, she's going to use non-determinism because she has an NFA specification to guess where the erroneous ID symbol might occur. So if agent 1 makes a mistake in this ID. Maybe he transitions incorrectly. Maybe he tries to cheat by just changing this from A to C, even though there was no head over that. The agent she can spot this and she can accept from her goal then, right? And these are going to be mutually exclusive goals. Agent 1 is just going to try to see the final configuration, a final state, and agent 2 is going to try to prove that the computation that led to that final state was erroneous in some way. She also has control over the alternating states. So I said before that the alternating states from those both have to accept, and so she can choose which one she wants to go on. So if you have a left successor and a right successor, she can say for example, right here, the next transition you make should be in line with the left transition. And if it is an alternating transition, the agent has to obey that. If the agent 1 has to obey that, if he doesn't, agent 2 can catch that as another mistake. That was I know, probably too technical, and I'm sorry for that, but it's just a high-level overview of this new reduction that shows that this NFA realizability problem is X-time complete. So here we can see that we have two different driving factors of this, right? And so I mentioned before that the AFA goals, I didn't show you this, and that's largely because they were a modification from the already known results of LTLF, right? So the LTLF problem is, the LTLF realizability problem is 2x time complete, and they have a linear transition between AFAs and LTLF. So I didn't see so much reason to mention this, although aside from the fact that, there are, again, some technical details that I'll link you to later if you're interested in seeing. But the interesting thing here, in my opinion, is that for DFA goals, the complexity is p-space complete. And that's really driven by the fact that you have n agents and you have to take the cross product. But for these other two, we can do reductions with just 2 agents. Really, the fact that you're playing a game with this very complicated specification that's very succinct, that's what's driving the complexity from here on out, right? So there's this dividing line here in which you have the cross product as being the kind of limiting factor. And then you have the fact that you might want to analyze this deviation, and you inherently have to play a game to analyze that. That drives the complexity over here. So the hardness from here comes from the n-agent case. The hardness from here comes from just the 2-agent case, and the upper bound agrees with that. So it seems like representation matters a lot when it comes to realizability, because aside from this cross product thing here, we would normally see an exponential jump. But it's not going to matter for verification, which I think is really strange, right? So as you can see in the left side of this column, we have p-space complete for all of these problems, and they're all going to be p-space complete. So let's see why that would be the case, right? But first, let's set up what the model looks like. So in this model, agents are going to come equipped with a goal, like before. That's going to be our temporal specification. But they're also going to come equipped with a strategy, which is a finite state transducer, like I talked about before. And they're both going to constitute part of the input, right? But I want to say something here really quick before I move on into the rest of this, which is that if we're dealing with an unbounded number of agents, then the input alphabet to both the strategy and the goal is going to be kind of a cross product between the action spaces of n different agents. So if we have n different agents and they each have 2 actions, for example, then that's going to be seen as kind of an exponential construction in itself, which makes it hard to do polynomial time reductions. So if we wanted to prove it was p-space hard, for example, we would have trouble proving that because writing down an exponential transition table. So how do we reason about this? Well, we wanted to look at a reasonable model that was a subset of this kind of bigger model that would naturally have a succinct representation, even though it had n agents. And to do this, we introduced this bounded channel property, right? So this bounded channel property kind of deals with this, is very much inspired by the properties of real distributed systems, and the fact that if we take this blue agent here in the middle, they really only communicate directly with these green agents who are their immediate neighbors, right? Now, these yellow agents also communicate with these green agents, and the green agents then communicate with the blue agents. So in a way, the yellow agents influence the green agents who influence the blue agents, but the blue agent is really only looking at these 3 neighbors and, of course, itself when it's deciding what to choose for its strategy, when it's deciding what to do for its goal, when it's deciding if its goal accepts or not. And this is what this does is that it means that the input alphabet for both the strategy finite state transducer and the goal automaton are not going to have these exponential alphabets. They're going to have a alphabet that just corresponds to these people. And if these people are a bounded number, if we can say there's a bounded number for every one of them, then they're going to be not an exponential construction overall for the transition table and the strategy and the goal automaton. So what does the reduction look like in this case? Well, we're going to reduce from the problem of whether a bounded space deterministic Turing machine. So before we did alternating, now we're doing deterministic, accepts the empty tape. And so we're going to have n cells on this tape, and each agent is going to basically be in charge of one of the cells. And they're going to output at each time step what that cell should read in the computation of this Turing machine. And the key point here is that in order to do that, you only really need to look at or be informed of what your two neighbors have, because you need to know if the head's moving in from the left to your position, or you need to move or from the right, for example. And if you're on the edge, then you only need to see this one neighbor here. And then that's enough information for you to determine what the cell should be at the next period of time. So this naturally gives us the bounded channel property. Each agent is only going to be looking at 3 cells, or 2 cells if it's on the edge. And that what gives us these small strategy and small goal representations that we need in order to make a proper polynomial time reduction from this p-space hard problem. And then also I'll point out that the goal of each, the specification for each agent, so specification for this agent which is in charge of this cell, for example, will just be to read a symbol or a final state, for example, that is corresponds to a unique accepting configuration. This, of course, if you say that there's a unique final accepting state of a Turing machine, it does not change the complexity of any of this stuff. So if we do this, then we can see that this can be done with any sort of automaton goal. It's very simple. It's just literally reading a single character. So this can be done with a DFA, AFA, or NFA. So that's where p-space hardness for all 3 of these models comes from. So now let's talk about the upper bound. The upper bound is going to be shown for AFAs, but that will then, of course, hold for all AFAs will hold for NFAs, which will hold for DFAs. And the basic diagram that we want to draw here is that we have an AFA, and we can exponentially blow it up to an NFA. And then we take the cross product of all the strategies, and we want to test basically this for non-emptiness. Now, you might be wondering, if I talked about the bounded channel property before, why am I talking about an unbounded cross product of n strategies now? And that's because in order to truly check whether your goal is met or whether you can deviate properly, and this, by the way, this general construction would work for both of them, you need to be informed of every strategy, not just the one that is on your bounded channel. Take the Turing machine example, or take the Turing machine reduction, for example. The agent who's in charge of cell 2 needs to be informed of what cell 3 is doing. But cell 3 needs to be informed of what cell 4 is doing in order to make their own output. And so to know the output at cell 3, you need to know the output at cell 4. That's why you need to take the cross product of all of them. So because we have the cross product of all these finite state transducers, then you get an exponential cross product to begin with. And then you maybe have an exponential blow up here from an NFA. If you have a DFA, if you have an AFA to an NFA. If you have a DFA, of course, you don't need to do any sort of blow up whatsoever. And then you could check this for non-emptiness. You get an exponentially large automaton, either an NFA or a DFA. And you can check that for non-emptiness, again, in kind of a similar way to what I showed you before, but in n log space. And so because n log space applied to this exponentially large automaton gives you np space, which is p space. So here are the final results for the multi-agent systems. And we can just see that the lower bounds here were shown through the bounded channel models, which are a special subset of the models that have a succinct representation. And we don't see any jump here, but we do see some jumps here. So I will go here really quick before I quickly transition to the second topic. If you do want some details about how those reductions work or anything, then it's here. There. So yeah, now I want to talk about succinct models for multi-agent systems in general. And the reason I want to talk about this is because, well, we had to specifically pinpoint this succinct model from another model. Like we had this general model, and we had to get this subset of these models that had a succinct representation, and that's what we used for our reduction. But also, I'd like to just point out that dealing with an explicit state space is really not something that's that familiar with kind of real computing systems. You deal with kind of a representation or something like that in some other way, or an encoding or something like that. So I want to talk about models that kind of uh, very naturally talk about the succinctness of these very complicated models that deal with cross products of different agents. So let's revisit this IBG model. Again, that was the model I showed you before. It was the one that was introduced by Gutierrez in 2015 et al. So I also want to point out here that there are no environment states here. The kind of state of the game could be thought of as the last setting to the variables, and there's no state space that's independent of that, right? If I did put in these environment states, then I guess the transition function would naturally become a little bit more complicated because I would need to specify which environment state I'm starting at, which cross product of actions I'm dealing with, and then which environment state I'm ending at. And that's going to be kind of complicated to write out as a transition table. So the IBG model largely gets around this transition table issue by just saying, well, the transition function is very simple. The state space can even be thought of as these variables, the settings of these variables themselves. So if you set a new thing to your variables, then you just go to that state, for example, right? So that's how they get across this problem of having this very large transition function, right? So here I wanted to kind of explicitly, not implicitly, put down just how that looks if we do want to put back the environment states. So if I want to reduce from L, which is a p-space complete language, or even just a p-space hard language, and generally speaking, that is what we're going to be dealing with, p-space and up, for these complexity classes, since we are dealing with n agents who are having a cross product between them. So that's generally going to be in p-space or above. Then I want to reduce from here to here, and especially if I'm doing the verification problem, I need to have, you can think of kind of a number of agents that's linear in the size of this input problem. Now, that's not kind of a formal statement I'm making. It's just kind of the strategy that would work for a lot of examples. For example, you could think of the n space of the n cell Turing machine naturally corresponding to the n agent game. But this naturally means that you're going to have at least two actions for each. You're going to have a cross product action space that is at least 2 to the n somewhere appears in there, right? Which means you cannot make a polynomial time reduction for that, right? So the idea that we want to talk about here is that, well, the IBG model got around that. It didn't make a transition table. It just said that the transitions kind of very easily follow from each other. And this is a very kind of natural and streamlined way to look at just a model where you have agents who have actions, and then the global action affects all the agents simultaneously. But it doesn't include environment states, and if I do include environment states, then I'm likely to have a large transition table. I don't want that, right? So I would like to say, where's a model where I don't have this large transition table, I do have environment states, and yet I somehow still have a small representation. So for all of this, I can just do it, right? Well, naturally speaking, a large class of models, just from an information theoretic perspective, are not going to satisfy this property. There are going to be some models that you just can't kind of compress down to a size. But taking kind of advantage of earlier work, or taking inspiration, I should say, of work from succinct graphs, I really think this is the way we should move forward with the representation of multi-agent systems. So this is going to be some kind of a future work that you can maybe see later from me, but it's not yet published yet. And the idea is that we want to encode everything. So we want to encode the states of the environment. We want to encode the states of the finite state transducers. We want to encode the states of the automaton that represents the goal in like a BDD way kind of way, or maybe just a circuit kind of way. And then our transition table will be this Boolean circuit that takes in the encodings of the two states. It takes in the encodings of the actions. It has some sort of Boolean circuit computation then, and it tells you whether this is the valid transition or not. In the same way that these kind of succinct graphs by Galperin and Widgerson would take a exponentially large graph, and the transition table, it wouldn't be a transition table, it'd be an edge relation. The edge relation would be then represented in this kind of way. You would take the encodings of the states, you would take this Boolean circuit, and then it would return whether the adjacency matrix would be a 1 or a 0. And the idea here is the same, but I think it's kind of maybe even better suited for this, right? because there are lots of natural multi-agent systems that are naturally going to have small circuits. Now, of course, if you take a random one, it's very likely not going to have a small circuit because that's just not how it works. But if you consider very important subclasses of multi-agent games, like for example, turn-based games, or maybe games where every agent doesn't necessarily act at every single state, but maybe like a maximum at a certain point, like maybe 3 agents act here, then 3 agents act here. So a generalization of a turn-based game, something like that, right? So all these types of things, or even the bounded channel models too, right? All these types of things will be characterized by transition tables that have a polynomial number of gates in the circuit, even though the very average case or the worst case scenario would have an exponential number of gates in the circuit, exponential in the size of the encodings, sorry, and polynomial in the size of the encodings, right? And so that's kind of future work. I don't want to speak so much more about that because it is something that will appear either in the review process or something else like that. So that's all I'll say about that now. So this is my final slide, and it's just the complexity results again from the multi-agent setting. And we can see kind of what drives the complexity. Well, sometimes it's the representation of the goal. Sometimes it doesn't matter at all. And it's a very strange picture. So yeah, that's all.
I was a little bit confused with the second half with this succinct representation. Imagine you have one agent, so the multi-agent thing is not an issue, just one agent and the environment. The succinct model that you're talking about in computer science is basically code, right?
Yeah.
So the two issues seem orthogonal, the multi-agent issue, the product issue, and the environment issue. And we somehow have a solution for each. So is it the idea that the two solutions don't kind of work well together?
Well,
or
they're not always going to work well together, right? Because if you just take a random system that has environment states and multiple agents, it's very unlikely that this is going to be have a small transition table.
But what is this system in the first place? It's for example, one agent and the environment. It's basically the code for that one agent that is that has conditionals, things like that, on what it observes from the environment, right? We are not.
The problem is the code for the environment. What is the code for the environment?
But the agent doesn't include the code for the environment.
But the environment has to make transition based on the.
Okay, then I can pretend the environment is also an agent, so same problem again.
Say again?
Then the environment becomes yet another agent, agent n+1.
There's a difference because the environment is the one place it doesn't make sense to say environment only interact unless we say turn-based game, which is one way to solve it. But if we have concurrent games, the environment interact with everybody. And specifying how the environment behaves in that case is going to be challenging because there are exponentially many actions, possible actions, right? And agents, exponentially many possible actions. So the normal way we say, well, it's a transition table from state of the environment, the profile of action to the next state, immediately give you an exponential size representation. So the answer is, really what the answer that you say is, we need to think about program for the environment as well.
Yeah.
So then you're saying in the one agent case, this is not an issue. It becomes an issue when I have n agents.
Concurrent multi-agent.
It is only an agent. It's only an issue when I have an unbounded number of agents, and so my global action space is going to be 2 to the n. If I have just one other agent, then if they have 2 actions, then that's just 2. So,
One other quick question: if already with deterministic finite automata things are bad, have you looked at subclasses of regular languages? They're kind of like a bunch of robust classes that would be under DFAs, and whether this kind of drops down in complexity.
no, I have not. The idea was just to kind of start with a temporal logic, and then think about the three types of automaton that would result from that. So you wanted to start from the LTLF and then take a translation from that. It's a good point, and it's something we could look at in the future, but it's not something I've done yet, so I can't speak intelligently to that.
They're kind of free automata, but I have not seen that they make any difference in complexity. This is a subclass of regular languages, counter-free automata, but I cannot recall
There is a whole hierarchy of them, right?
Mhm.
So
Not so much within, yeah, but it will be interesting to look. I have not seen that they make a difference in complexity.
So when I started looking at some results in the area, I always had some doubts on the different parameters, if they are just as important. So I think you kind of outlined some of this, for example, like the number of agents. So, like, for example, like I think the DFA case, I don't know, like, does it decrease if you fix the number of agents, the
Yes.
complexity?
Yes, it would go to polynomial time.
It will go to polynomial time, right?
If I fix like 3 agent.
I mean, this kind of stuff, I think it's important to also know, right? Yeah. So like typically when people talk about it, they just say like, okay, any number of agents, and they don't really. I think the other thing that I thought was quite important is also like the size of the specification. I mean, is it really that big in practice? And do people like, because I think the setting always just says like, okay, I mean, it's part of the input, right? And but I mean, if you look at verification, like LTL verification, I mean, if you fix the LTL formula, it's polynomial, right? So, I mean, is it really that big in practice? I don't know. I mean, like, when I look at the area, they just say like, okay, everything is just as big, right? So
Right.
the data complexity, is it really important? Like, or, I mean, I just want to ask here is, I understand this is like a framework to understand stuff. It's just that I have some doubts on, if all parameters as important, so.
Yeah, no, I totally agree with you. And that's also something that we're looking at in kind of the succinct models too. So the idea is that, a lot of these reductions, for example, will be from LTLF. And if you have an LTLF specification, they'll just say, well, if you have an LTLF specification to start from, then you're going to be, for example, p-space hard. That if you're doing like a verification or something like that, right? And that's just driven by the fact that you can have larger and larger and larger LTLF specification. I don't think that's a realistic thing in practice, as you said. So we're actually kind of that's another thing we're looking at. So I don't know how much I can speak about it, but it's just kind of this thing. Well, what if you had kind of you fix this parameter and you vary another parameter, right? It's the kind of like old school complexity theory where they used to do parametric stuff. I'm very interested in that. As for how it actually runs into practice, I can't really speak to that. What I do is kind of just fix one parameter and then vary another and then show how the complexity changes from that. But you are completely right in the fact that, fixing the size of the specification and then varying, other stuff is incredibly important. And it's something I'm looking at right now.
Where's the mic?
This has been a weakness of the field, I think, for many years. Okay, take for example the classical result, the founding result. Model checking is linear in the system and in the specification, right? But it's in the explicit set of the system. Okay, nobody thinks about systems in terms of explicit states. A system is a program, and so you really need. So the answer is, it always has been, what is the complexity if you take the representation of the system? So the property, yes, is small, but the system is going to be giving you always succinctly in terms of some program. But it's usually not in the way we analyze it. So if you look, for example, at linear time model checking, we usually say it's linear in the system and exponential in the formula. But it's really exponential in both. So the field suffers from not having just very, very clear. And this is the beginning of a conversation, try to be a bit more realistic about, okay, what is the size of what are the input parameters and what exactly is the realistic way to measure their size. Okay, let's say, last question.
As a follow-up to your statement, once you change the representation and you come up with a kind of symbolic representation for the transitions, the complexities that you were presenting here are likely to completely change.
Yes. Yeah, that's kind of what the end of the talk is going to say, that wait for a more realistic analysis would be when we are having, to me, the idea of succinct representation is not an esoteric object. It's actually the realistic object. Most systems are given to us by program. So it's a succinct representation. That's how we define program. If you have to spell out the precise the state space, it's just not doable unless you're doing a very artificial small example. Okay, let's thank Senthil.